big problems with radiation is that people just hear the word and immediately assume that it's bad. They think that all kinds of radiation are bad for you. People don't buy microwaves because they think it's going to give you cancer, all these kind of problems. So in terms of radiation, there's two big aspects that you need to consider. One is ionizing radiation, and the other is non-ionizing radiation. So generally you would think that something that is a non, it doesn't do it, is generally the better option. And in this case that is true. So we like non-ionizing. This means it doesn't have the electrical charges, the ions, to strip away particles and destroy DNA and affect the body, which is ultimately what causes the damage. Ionizing does. So this is the bad kind of radiation. This is the stuff that people should be worried about, or at least be careful with. This is the stuff that we should treat respectably, but it's not dangerous. We don't need to be afraid of our mobile phones, of our microwaves. So when we talk about these types, ionizing, we have alpha radiation. That's a very ionizing. We've got the beta, that's reasonably ionizing, and we've got gamma radiation, which is less but very high energy. We also have, in terms of our radiation, we've got UV radiation. So we've got UVB and UVC specifically. So I'll write B/C. They're the bad ones. There are A, B, and C types of UV radiation. We don't cover them, but B and C are the bad ones. That's the stuff coming off the sun that really damages the body. We also have X-rays. X-rays are also a very ionizing type of radiation. Very, very high energy, can do a lot of harm. If we go over to the non-ionizing, however, these are types of radiation. And remember that radiation is part of the electromagnetic spectrum. So if you look at the electromagnetic spectrum, you can see everything that has very, very high energy, your radiations, your UV, your X-rays, are the stuff that can strip atoms and destroy the DNA. They're the bad ones. We look at the lower types of energy, we've got things like the microwaves. We've got the visible, so visible light spectrum. That's certainly not ionizing. The stuff that we see every day isn't giving us cancer. We've also got infrared. So this is the one that most of your remotes and things will use. Your TV remote doesn't give you cancer. Non-ionizing type of radiation. We've also got radio. And finally, we've got UVA. So radio waves. So this is a lot of your transmissions, so things like your TV, old school two-way radios, all that kind of stuff. Anything that uses communication based, that's a radio type or radio spectrum of radiation. It's still a radiation, but these are non-ionizing. So sure, they can pass through objects, they can travel through vacuums, etc., but they don't have the energy required that these ones have to actually destroy the body or cause any harm. So microwaves is your mobile phone. Your mobile phone is predominantly producing and using microwave radiation. That's why sometimes you'll find, apart from the fact that the thing generates heat as a result of the electricity and the battery, if you talk on the phone with it to your ear for a long period of time, you find your ear gets really hot. That's a result of the microwave effect. The microwave radiation is affecting your body and it's warming it up, but it doesn't have the energy to actually alter your DNA and give you cancer in the ear from using your phone too much. If we look at the ionizing effects of radiation, one of the things to consider is what we call the absorbed dose. So that's how much you actually absorb from an exposure. There's two things that you would need to think about. So when we talk about the absorbed dose, that's going to be equal to. Now, obviously, depending on how much energy the thing has, depends on how much energy, how much radiation the body absorbs. So we need to know how much energy is absorbed by the tissue itself. So we would say it's the energy absorbed by, and when we say tissue, we're just talking about skin, etc., etc. Any contact of the body. So the energy absorbed by the tissue. That's the whole thing. Now we need to think about how much tissue is there. So if I was exposed to just my hand, there might have been a lot of energy per tissue, but there's only a very small area there. So that's a big issue. But if I was exposed to the same amount across my entire body, it's distributed. So it's like diluting something in water. You thin it out. So we would divide this by the mass of the tissue. And that is our absorbed dose. So how much energy is absorbed, and we divide it by the mass of the tissue, how much of the tissue is spreading it out. And that will give us an absorbed dose. Often you'll see this referred to as joules per kilogram, which is our common SI unit. How much energy for every kilo of mass, or sorry, every kilo of tissue, which makes sense. Energy over mass, joules per kilogram. So that's the absorbed dose. Sometimes they'll often use the term grays with an A after the guy, and they use the symbol GY as a symbol of grays. So grays, if you ever hear, is talking about an absorbed dose. Joules per kilogram is the common SI term, but often, especially Americans and some of the Soviet stuff that you hear, they often refer to grays among with other units. Now if we look at the properties of ionisation, so what do we need to consider when we're worrying about how dangerous something is, how ionising a substance is, and how much effect it's going to have on the body? Some of the things to consider are, what is the mass of the object? So if there's lots of it, that's a bigger issue than if it's a very small amount of it. What is the charge? So is it highly charged? Is it slightly charged? Does it have no charge? That's going to affect it. How much energy does it have? So if we look at something like the gamma radiation, which has a very large amount of energy, that's a big issue. Alpha, while potentially dangerous, has a very small amount of energy, so it's not nearly as harmful as the gamma radiation is. Penetrating power. This is all about how far it can pass through an object. We need to factor that in based on special equipment. What do we need to wear when we're dealing with this? What kind of walls, buildings, and shields do we need if we're using this kind of stuff? And also, how much of a risk is it to the body? So if I'm just exposed to it in the air, is it going to get into my vital organs and cause issues? Or is it basically going to be stopped by the surface of my skin, trapped in the mucus of your mouth and saliva and all that kind of stuff? Or is it going to pass straight through you? Ionizing ability. So this is talking about how much can it ionize. Is it a very ionizing thing like our alpha particles? Or is it less ionizing like the other two? So that's another factor to consider. When we look at the three options, alpha, beta, gamma, in terms of the mass, that's going to change a bit. Mass of alpha particle is heavy because it's a helium nuclei. Right? It's got a proton and a neutron. So that has mass. So this is quite heavy in context. Beta radiation, remember, was just that electron. So I'll say this is light because it's just an electron. And electrons are very, very light in comparison to the nucleus. And lastly, gamma. Remember, gamma is virtually just high energy light. So this has no mass. No mass. It is weightless. Or weightless is probably not the right term, but it has zero mass. It moves at the speed of light. Then if we look at things like the charge. Alpha. What is it? It's a helium nuclei. So it has a charge of +2. Beta radiation is that electron, so it has a -1 charge. Obviously this is all to do with what it's made of. So if we look at the helium, has 2 protons, no electrons, so it's going to have a +2. Just an electron, so it's going to have a -1. And gamma has 0 charge. No charge, no mass so far. So far gamma is really boring. When we look at energy, for example, this can be affected. You can have various energy gamma depending on how you create it. So things like radiation sources in the medical industry, we can affect that. We can put more energy in to create a higher energy gamma ray. But penetrating power, this is the more important one. When we look at penetrating power, for alpha, we're talking a very small amount. So it's actually around 0.01 millimeters. So not much at all. So the skin, a piece of paper, quite easily stops alpha radiation. When we go to beta radiation, we're talking a few millimeters. So still not much, a few millimeters. It's enough to get through the surface of your skin. A thick piece of cardboard will probably stop it. And then when we go to gamma, we're talking in the caliber of meters. So unless we've got something very dense like lead or something very thick and solid like concrete, it takes meters and meters of material to stop gamma radiation from passing through, to slow it down. Ionizing ability. So, alpha, we said it's very high. So, ionizing. I'm going to use 3 arrows to signify very ionizing. Then if we go to beta, it's okay. So we'll just say reasonable. Maybe give it 2 arrows to be generous. 2 out of 3 arrows. Good Yelp review. And then gamma is sad. I'll give it a half arrow. One generous customer gets a half arrow on its ionizing rating. So gamma, not very radiating at all. Beta, it's reasonable. And alpha, very ionizing. 3 stars. When we talk about the effect of ionizing radiation on the body, there's 2 aspects to it. 2 ways that we can look at how it's affected. We've got the somatic effects and we've got the genetic effects. So the somatic effects are more like the physical, more immediate effects that you can see or feel as a result of the radiation. The genetic effects are the ones that are actually affected in your DNA. So with your genetic effects, these are talking about actual mutations in the body. So the radiation will cause your cells, your DNA to mutate. Something will change in the code, and that can be passed on to your children and so on and so forth. So you can actually create a mutation, and your children will have it, their children may have it, all these kinds of things. This is one of the big problems they've had with some of the nuclear problems, like in the Chernobyl disaster, is that the children today are still being born with all of these defects as a result of the nuclear radiation that they experienced all that time ago. So if we look at some of the somatic effects, you can get things like nausea. So that's a sign of radiation sickness, is you can feel quite nauseous. White blood cells can also be affected. So these will go up. The white blood cells will increase. This is a sign that the body is fighting something. When your white blood cells are very high, it means that they're fighting something. So generally you've got an infection, a disease, whatever. In this case, they can be spiked by the somatic effect from radiation as a side effect of your radiation sickness. At a higher dose, you can also get things like hair loss. You can get vomiting. Double M. So hair loss and vomiting at the higher dosages of radiation. You can also get rashes or burns to the skin, just like when you get sunburn. When you get sunburn out in the sun, you are getting radiation burns. That's a somatic effect of ionizing radiation. It's burning your skin. You can also get, quite simply put, death. You can die. At very high doses, it'll kill you. When we look at genetic effects, we can talk about mutations. So this is the DNA actually being altered in some way. You can have birth defects. Obviously you can get tumors and cancers. So these are genetic effects. These are things that are affected in your DNA, and you can subsequently pass these on. These things you won't pass on. You can't pass on death. You can't really pass on hair loss, vomiting, rashes, burns, nausea. But these are things that will affect you, and you'll feel, you'll see, etc. So they're the 2 ways that radiation can affect the body.